So in the last class, we have seen how the relationship between the energy and the length of the vector can be found. Then after that, we have seen some other relationships where the product of two signals, when it is integrated over 0 to t, we can write it in the as inner product of Si and Sk as Si transpose into Sk. Okay, and then the second relationship where we have found the Euclidean distance. Okay, so here we have found the Euclidean distance between two vectors. To find the Euclidean distance, this is what the formula we have. This formula I have shown you how to derive from the energy equation. Okay, so that is how, see, you need to remember these equations. Okay, then between these two vectors, I can also find the angle. Okay, so to find the angle, the equation is cos theta ik is equal to Si transpose Sk divided by length of Si and length of Sk. Okay, and if theta value is equal to 90 degrees, then Si transpose and Sk will be equal to 0. Okay, so this is what we have seen. And then after that, I've started the new derivation. It is nothing but the Squarge inequality. So here, according to the Squarge inequality, what I need to show here is when you multiply the energy signals S2 and S1 of t and S2 of t, and integrate it from minus infinity to plus infinity and square of that, it will be always less than or equal to energy of S1 of t and energy of S2 of t. Okay, so this is nothing but the energy of S1 of t and this is nothing but the energy of S2 of t. Okay, and this equation, see here, this equation says that it will be always less than or equal to. So if I want to get equal to sign, equality holds good only when S2 of t will be equal to CS1 of t. Okay, so this is what I need to prove. So in order to prove that, first I have represented S1 of t and S2 of t as a linear combination of orthogonal basis functions, and this is a orthogonal basis kind of orthonormal basis function condition, and then I have represented it graphically, geometrical representation. This we call it as geometrical representation. Then here theta is nothing but the angle between S1 vector and S2 vector. So here I will try to find the angle between S1 vector and S2 vector. So from the previous equation, we know that this is what the formula. Okay, and then we also know Si transpose into Sk can be represented as you need to multiply Si of t signal Sk of t and integrate it from 0 to t or from minus infinity to plus infinity. Here I have extended its axis. Okay, then in the denominator, Si is nothing but the energy of Si of t and energy of Sk of t whole power half. Okay, so this I have taken from the first equation. Okay, then see, this is for Ik. Okay, so if I want to find for S1 and S2 specifically, then same thing. I have replaced with 1 and K I have replaced with 2. That's all I have done. And then I have substituted the equation, and we know that the cos theta, the minimum value is -1 and the maximum value is +1. If I take mod, then it will be always the cos theta value will be always less than or equal to 1. Okay, so here cos theta, whatever cos theta equation I have just substituted in this equation, so that I have got in this way. Okay, then cross multiplication I have got in this way. Now what I need to do, okay, so here I have to square. Yesterday I didn't square it, so square on both sides. So when you square on both sides, it will become integral minus infinity to plus infinity S1 of t into S2 of t dt whole square, which will be less than or equal to square on both sides. This side I have squared, this side also I will square. If I square, the under root will be under root and square will get cancelled, so I'll be just left out with integral minus infinity to plus infinity S1 square of t, which is nothing but the energy of S1 into energy of S2 of t signal. Okay, S2 of t signal. This is my equation A. Okay, so when you compare this equation A and whatever I need to prove, they both are same. Okay, so this is what I need to prove, right? So integral minus infinity to plus infinity S1 of t S2 of t dt whole square, which is less than or equal to energy of S1 square, S1 of t and energy of S2 of t. The same thing. This is proved. Okay, so this is what Squarge inequality equation. So you can say that hence proved. Okay, and you have one more condition also, like see, less than is fine, equal to, this will be equal only when here S2 of t will be equal to CS1 of t. In order to prove this, what I will do, in place of S2 of t, I'll just substitute CS1 of t. Okay, cos theta. In cos theta, what is the cos theta? Cos theta equation is, I have cos theta equation as, okay, I'll write the equation, integral minus infinity to plus infinity s1 of t into s2 of t dt divided by integral minus infinity to plus infinity s1 square of t dt into integral minus infinity to plus infinity s2 square of t dt. Okay, here what I need to do, I need to substitute s2 of t as c s2 of t. Okay, that's all. If you substitute s2 of t as c s1 of t, then it will you'll whole power half is also there for this, whole power half, here also whole power half. Okay, so when once again somebody is in lobby, okay, nobody is in lobby. Okay, fine. So this is the equation for cos theta. Okay, so this is equal to what I need to do. This equality sign holds good only when s1 or s2 of t is equal to c s1 of t. So what I'll do, I'll just substitute this in this. Okay, so it will be minus integral to minus infinity to plus infinity s1 of t, s2 of t. S2 of t is nothing but c s1 of t dt divided by integral minus infinity to plus infinity s1 square of t dt whole power half into integral minus infinity to plus infinity. In place of s2 of t, I have to substitute cs1 of t. So cs1 of t whole square dt whole power half. Okay, so this will be equal to integral minus infinity to plus infinity. Anyway, c is a constant, I'll take it outside. s1 of t into s1 of t, it will be s1 square of t dt divided by integral minus infinity to plus infinity s1 square of t dt whole power half. Here integral minus infinity to plus infinity c square, I'll have c square s1 square of t dt whole power half. Anyway, c square is a constant, I can take it out. C square whole power half I'll have, so c square whole power half I can write as c integral minus infinity to plus infinity s1 square of t dt divided by integral minus infinity to plus infinity s1 square of t dt whole power half into c square. This c square I can take outside like this. Okay, I'm just trying to simplify here only c square. So c square whole power half will be c. Okay, I'll take c outside. So I'll be just left out with minus integral to plus integral s1 square of t dt whole power half. Okay, so now I can use the formula a power m into a power n formula. This c and this c will get cancelled. Here this is same. Okay, and this is also same, and I have half half. Okay, so a power m into a power n will be equal to a power m plus n. Okay, so power here is nothing but half plus half, it will be 1. So I'll be just left out with, this will be equal to integral minus infinity to plus infinity s1 square of t dt in the numerator divided by, when you multiply this and this, the base is same. Okay, and the power is half here and half here. So I can write m plus n. So half plus half, it will be 1. So minus infinite to plus infinite s1 square of t dt. Okay, so this and this will get cancelled. So I can say that cos theta is equal to 1 only when s2 of t is equal to c times of s1 of t. This is what I have proved, but see, in the exam and all, you need not prove that. You can just write the condition. Okay, otherwise you need to do it until here. Okay, until here, whatever I've written in the notes, you can follow the same thing. Okay, until here, and you can say hence. This is very, very important derivation for the sake of exam also, for the sake of external also. Is it clear? Is this clear? Have you understood?
Yes, ma'am.
Yes, ma'am.
Anybody want
Yes,
me to
ma'am.
repeat somewhere? You can ask me. Okay. Otherwise, I'm going to the next. Here, if the signals are complex valued, again one more relationship. Okay. This also we need not prove. Other relationship related to Scotch inequality. Other relationship related to Scotch in Scotch. Yeah. Scotch inequality. Okay, this also we need not prove. Okay, so this is only the statement I'm giving. So if one of the signals are complex valued, then we can write as minus integral integral minus infinity to plus infinity s1 of t into s2 star of t. Okay, conjugate. Okay, dt modulus. You may ask me a question, ma'am. Here you have not taken modulus. Where it is? Mod here you can write it. Okay, but anyway, since we are squaring, either you have the mod or you don't have the mod, it's okay. Okay, so that's the reason I didn't concentrate much on mod here. Okay, it will be less than or equal to integral minus infinity to plus infinity mod s1 of t whole square dt whole power half into integral minus infinity to plus infinity mod s2 of t whole square dt whole power half. Okay, and here also the equality holds good only when s2 of t is equal to c times of s1 of t. Okay, now this we need not put. This we need not put. Okay, so this is just the statement I'm giving you. Okay, hope this is clear to all of you. I've not done anything. I've just given you the statement here. That's it. Okay, fine. Now I am going to the another important, very important topic. It's very important for the sake of exam. This exam also, final exam also, very important. Okay, so this no question paper will be there without this question. Okay, the next topic is Graham Smith. One second, I'll write it properly. SCHMIDT Gram-Smith orthogonalization procedure. You have problems also related to this. It is very important. Theory is also important. They may ask you to explain Gram-Smith orthogonalization procedure. So whatever I'm going to do now, you need to do everything. Okay. Okay. So what for this Gram-Smith orthogonalization procedure is used? So if you just recall, I have written the signals S1 of t or Si of t in general as a linear combination of orthonormal basis functions. Okay, so there I'm saying that orthonormal basis function. Okay, so this Gram-Smith orthogonalization procedure will help you to determine the orthonormal basis functions. Okay, so to determine the orthonormal basis functions, we will use this Gram-Smith orthogonalization procedure. Orthonormal basis functions can be obtained using this procedure. Okay, so how we are going to derive them, that we'll see now. Okay, otherwise this this Gram-Smith orthogonalization procedure will help you to obtain the orthonormal basis functions. Okay, so why we are finding orthonormal basis functions? Because we'll be able to represent the energy signals using this not orthonormal basis functions. Okay, since we are able to represent the modulated signal using the orthonormal basis function, so we are in need to find the orthonormal basis functions. Okay, so how to find that, we'll see now. Okay, so let us consider that I have mi symbols. Okay, for each mi symbol I will have si of t. Okay, mi symbol where I is equal to 1 to m. Okay, and now let us assume that there are n orthonormal basis functions, phi 1 of t, phi 2 of t, so on. Phi n of t are the orthonormal basis functions. Orthonormal basis functions, orthonormal basis functions. So I will be able to represent Si of t in terms of this orthonormal basis functions. Okay, so how will you represent Si of t is equal to Si1 phi 1. These all equations you know already. I'm not doing anything here. Plus Si2 phi 2 of t plus so on plus Sin phi n of t. Phi n of t. Okay, so where this I can in short write as Si of t is nothing but summation j is equal to 1 to n Sij phi j of t. Okay, so these all equations are not new for you. It is very old equations only. Okay, so now I'll write individually for S1 of t, S2 of t, S3 of t, like that. Okay, so first let us write for S1 of t. It means that I value I've taken as 1. Okay, when I value is equal to 1, in the sense for M1 symbol. Okay, for M1 symbol I'm writing S1 of t. So for M1 symbol I is equal to 1, S1 of t will be equal to S11 phi 1 of t plus S12 phi 2 of t plus so on plus S1n phi n of t. Okay, and if I want to find S2 of t, then it will be equal to S21 phi 1 of t. See, you have to remember these equations. Remember, very important to remember. Okay, plus S22 phi 2 of t plus so on plus S2n phi n of t. In the same way, I have to find for S3 of t, so on, like that, Sm of t, because I have how many symbols how many symbols I'm getting, that many modulated signals also I'll get. Okay, so Sm of t will be equal to Sm1 phi 1 of t plus Sm2 phi 2 of t plus so on plus Smn phi n of t. Okay, so let me name this equation as 1, 2, 3, like that. Not 3, mth equation. Okay, let us assume these are my equations. Okay, and see, I will be able to represent S1 of t, S2 of t, Sm of t in this form only when this phi 1 of t, phi 2 of t, phi n of t are orthonormal basis functions. Okay, so what is the condition for orthonormal basis functions? We already know that. Integral 0 to t phi I of t into phi j of t is dt is equal to 1 if I is equal to j and is equal to 0 for I not equal to j. Okay, this condition it has to satisfy. Okay, only when this condition is satisfied we'll be able to represent the modulated signal in as a linear combination of basis functions like this. Okay, so here the main goal of this Gram-Smith orthogonalization procedure is I have to find phi 1 of t, phi 2 of t, phi n of t, all this I need to find this orthogonal basis functions. Okay, and whatever basis functions you are finding, it should satisfy this condition as well. Okay, so in order to find the orthonormal basis functions, in the sense here the goal is to find phi 1 of t, phi 2 of t, so on, phi n of t. These all I need to find. Okay, so first we'll try to find phi 1 of t. Okay, so in order to find phi 1 of t, step 1, I'll take first step. Step 1, to find phi 1 of t. To find phi 1 of t, what I need to do is I need to set all the parameters, all the coefficients. All the coefficients. What are the coefficients? here I have S11, S12, so on, S1n are the coefficients. Okay, so in order to find phi1 of t in the first equation, what I'll do, except this S11, I will make all other terms to 0. Okay, only when I make all other terms to equal to 0, I'll get phi1 of t. Okay, so for first phi1 of t, I need to make other coefficients as 0. To find phi2 of t, first two coefficients should not be 0, our rest all should be equal to 0. If I want to find S3 of 3 coefficients I need not make 0, rest all coefficients I need to make it 0. That is how this procedure will be. Okay, so the procedure is to find phi1 of t, set all the coefficients. One second. All coefficients equal to 0 except S11. Okay, S11 in equation 1. Okay, which is my equation 1? This is my, where it went? No, this is my equation 1. Okay, in this equation 1, I need to set all other coefficients is equal to 0 except this S11. This S11. Okay, so in that case, what happens here? Equation 1 now becomes as S1 of t is equal to S11 phi1 of t. Okay, plus rest all terms will be equal to 0. So I need not write those terms. Okay, why it is 0? Because here I'm taking the condition that if I want to find phi1 of t, I need to set all other coefficients is equal to 0. Other coefficients are nothing but Sij coefficients. Okay, like S1, S12, S13, S14, like that. All other coefficients should be equal to 0 except S11. Okay, so this is what the procedure. So I need to just take S11 value and rest all values should be equal to 0. So S1 of t will be equal to S11 into phi1 of t. Or see, what is my goal here? I need to find all the orthonormal basis functions. So what is it? Phi1 of t I can write as S1t divided by S11. Okay, S1t divided by S11. So I will be having this S1 of t, and I have found by using integral 0 to t Si of t phi j of t dt. Okay. Okay, I'll do it in the other way. Instead of using this formula, I'll directly what I'll do here, this I'll name as equation 1. Okay, so here I've got phi1 of t as S1 of t divided by S11. I'll be knowing S1 of t, but I don't know what is S11. So I need to calculate what is my S11 as well. Okay, so in order to calculate S11, what we'll do, square your equation 1. Okay, I'll write as a because I'll get confused with that one and this one. So square your equation a and then integrate it from 0 to t. So in that case, what happens? Okay, when I square it, it will become phi1 of t square. First I'm squaring it, so S1 square of t divided by S11 square. Okay, so now what I have to do, I have to integrate also. So minus integral 0 to t phi1 square of t, which is equal to integral 0 to t S1 square of t in dt. Here dt S11 square dt. Okay, anyway, this is independent of dt. I can take it out. So I can write this as integral 0 to t phi 1 square of t dt, which is equal to 1 by s11 square integral 0 to t s1 square of t dt. Okay, so now what I'll do, I will just cross multiply. So s11 square is equal to integral 0 to t s1 square of t dt divided by integral 0 to t phi 1 square of t dt. What is this? What is this? What will be the value of this? Integral 0 to t phi 1 square of t dt. According to the orthonormal basis function, like orthonormal, the condition is phi I of t into phi j of t dt is equal to 1 when I is equal to j. Here I is equal to j is equal to what I have? 1. So it is integral 0 to t phi 1 of t into phi 1 of t dt. Okay, so phi 1 of t is nothing but integral 0 to t phi 1 square of t dt. Okay, phi 1 square of t dt will be equal to 1. Right? Are you understanding what I'm trying to do here? Are you all understanding what I'm trying to do here? Tell me the answer.
Yes, ma'am.
Anybody has any doubts? Jyoti? Jyoti?
Yes, ma'am.
Is it clear, ma?
Yes, ma'am.
Okay, fine. Okay, so here what I'm doing, I will make this value as 1. Okay, the reason for making this value equal to 1 I've already explained here. So you know the condition for orthonormal condition, it is from 0 to t phi I of t into phi j of t dt will be equal to 1 only when I is equal to j. Okay, here I have made I is equal to j is equal to 1, so it will become as phi 1 of t into phi 2 of t, so which is nothing but integral 0 to t phi 1 square of t dt, which is equal to 1. Okay, so this entire thing I'll substitute in this previous equation. Okay, so it will be equal to integral 0 to t s1 square of t dt divided by 1. Okay, it is 1 since we know that integral 0 to t phi 1 square of t dt is equal to 1. This you can write. Okay, so here s11 square will be equal to integral 0 to t s1 square of t dt. Okay, so where s11 is equal to under root of integral 0 to t s1 square of t dt. What is this? It is nothing but finding the energy. Okay, so I can replace this portion with root e1. E1 indicates energy of signal s1. Okay, so now I'll name this as equation B. Now what I'll do, I'll substitute B in A, so that substitute B in A. Okay, so that phi 1 of t, A equation is nothing but this equation, phi 1 of t is equal to s1 of t divided by s11. Okay, so phi 1 of t is equal to s1 of t is equal to s1 of t s1 of t divided by s11. Okay, but what is s11? We have s11 is nothing but root. Okay, I'll write as integral 0 to t under root of integral 0 to t under root of integral 0 to t s1 square of t dt, which I can also write as s1 of t divided by root e1. Okay, so just by using if I have s1 of t, I can find the energy of that signal. So that energy of that signal will be equal to under integral 0 to t s1 square of t dt. Okay, so by using S1 of t and the energy of that particular signal, we'll be able to find the orthonormal basis function phi1 of t. Okay, any doubts you have in this until here? Until here, if you have any doubts, you please ask me. Any doubts you have until this portion? Okay, fine. Nobody is responding, so I'm assuming that it is clear to all of you. Anybody want me to repeat once again? Because this is very, 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 very important. Anybody want me to repeat? Anybody want me to repeat? Okay, nobody is responding, so I am thinking that nobody wants me to repeat, but still I will repeat for my satisfaction. So this Gram-Smith orthogonalization procedure, it will help us to calculate phi1 of t, phi2 of t, phi-n of t when you have the modulated signal. Okay, psi of t is nothing but the modulated signal, and we know that we can represent this modulated signal by using orthonormal basis functions in this way. Okay, so that further I have represented for each symbol. So S1 of t, this is what the equation, S2 of t, this is what the equation, S3, Sm of t, this is what the equation. Okay, so the condition for orthonormal basis function is it has to satisfy integral 0 to t pi of t into pi j of t dt should be equal to 1 if I is equal to j, and it should be equal to 0 when I not equal to j. Okay, this condition should be satisfied. Only when this condition is satisfied we'll be able to write in this way. Okay, so this condition should be satisfied. Okay, and coming to the Gram-Smith orthogonalization procedure, the mean what it will do is it will help us to find phi1 of t, phi2 of t, phi3 of t, phi4 of t, so on like that until phi-n of t. Okay, where this n is always less than or equal to m. Okay, number of orthogonal basis functions required will be always less than or equal to number of symbols generated. Okay, so in order to find phi1 of t, first what I have done, I have taken it as step 1. Okay, in the step 1 what I did, I have considered equation 1. Okay, equation 1 is nothing but this equation. In this equation what I did, I have taken all other coefficients, s1 of t, s1, s12, s13, s14, s1n, all these are nothing but the coefficients, right? So all these coefficients I'm making it to 0 except s11. That is what the condition I've considered. So I've got the equation after making other coefficients as 0. This is what the equation I've got. From this I can write as phi1 of t is equal to s1 of t divided by s11. Okay, so we will be knowing s1 of t, but what will not know s11. So in order to calculate s11, what I have done here only, I have squared equation 1 on both the sides, so I'll get pi1 square, s1 square, s11 square. Okay, I have squared on both sides, and then I have also integrated from 0 to t on both the sides. So this is what the equation I have got. Okay, now s11 square is a constant value. So since it is a constant value, real valued number, it is a real valued number, so it is independent of t, because here the integration is done with respect to t, so this will be independent of t, so I can take it outside. So it is 1 by s11 square integral 0 to t s1 square of t dt. Now what I have done, I have just cross multiplied so that I could write in this way. Okay, so from the orthonormal condition we know that integral 0 to t phi1 square of t dt is equal to 1, so that I have substituted. So finally I've got s11 square as integral 0 to t s1 square of t dt. Okay, but I want only s11, not s11 square. So what I have done, I have taken root on both the sides. So s11 is equal to root and square will get cancelled in the left hand side, and this side I'll have integral 0 to t s1 square of t dt. Okay, we know that this is nothing but this will give me the energy of the signal. So since it is the first signal s1 of t, I'm representing that energy as given. So this I've considered as equation B, and this equation B I've substituted in A. Okay, all these calculations I've done only to find out S11. Okay, so that is the reason what I have done. I've got S11 equation. So now I'll substitute it in this. So phi1 of t will be equal to S1 of t divided by S11 is nothing but root E1. Root E1 is nothing but the energy of S1 of t signal. Okay, so that is what I have represented. The final equation to calculate the orthonormal basis function is this. This is what the equation to calculate the first orthonormal basis function. Okay, so now I'll go to the next step. Okay, next step 2. Step 2, I have to find phi 2 of t. To find phi 2 of t. To find phi 2 of t, what I'll do here, except S11 and S12, except sorry, I'll to find phi 2 of t, I'll consider the second equation. Okay, so to find S1 of phi 1 of t, I've considered the first equation. To find phi 2 of t, consider the second equation. Okay, so S21, S22, except S21 and S22, make all other coefficients such as S13, S14, so on, S11, not S1, no, it is 2, S23, S24, second equation. In the second equation, these are the coefficients. Except S21 and S22, rest all should be equal to 0 in equation 2. Okay, so what happens to equation? First, let me write. We know that the equation 2 is equation 2. I'll write the equation 2 first. It is nothing but S2 of t is equal to S21 phi 1 of t plus S22 phi 2 of t plus S32 S23 phi 3 of t plus so on plus S2n of phi n of t. Okay, so these all terms I'm making it as 0 because I'm making S23, S24, S2n as equal to 0. So 0 into anything will be equal to 0 and all addition of zeros will be 0. So I'll be left out with after substituting S23 is equal to S24 is equal to S2n is equal to 0. This equation I'll name as equation A. Equation A turns to S2 of t will be equal to S21 phi 1 of t plus S22 phi 2 of t. S22 phi 2 of t. Okay, so this I'll name as equation B. Okay, this I'll name as equation B. Okay, so now what I'll do, see what I have to get phi 2 of t. Okay, so phi 2 of t I can write as phi 2 of t is nothing but okay, first what I'll do, I'll shift this term to the other side. So I'll be just left out with I'm just rearranging the terms. So S22 phi 2 of t is equal to S2 of t minus S21 phi 1 of t. Okay, this I'll name as equation C. Okay, and this S22 phi 2 of t I will also name as G2 of t. Okay, just I'm giving one more name here. Okay, now what I'll do, I have to get phi 2 of t, that I'll see later. Okay, first so what I'll do, I'll take this function S2 of t b. I will do some like further analysis by multiplying something to get phi 2 of t. Okay, in order to get that, what I will do, I will just multiply Okay, this equation I'll write later. This equation also I'll write later, because again let me finish whatever modifications that should be done to this equation B. Let me do that and then I'll write this equation. Okay, so here what I'll do, I'll multiply both sides with phi1 of t and integrate it from 0 to t. Okay, so first what I need to do, and I have to multiply left hand side and right hand side with phi1 of t, and then after that I have to integrate from 0 to t. So the equation will turn to, first I'll multiply phi1 of t on both the sides is equal to s21 phi1 of t into phi1 of t, okay, plus s22 phi2 of t into phi1 of t. Okay, so after this what I need to do, I need to integrate also. See here I have to multiply on both the sides with phi1 of t. So here what I did, for individual term I have multiplied, or else I'll write one more step, no problem. I have s22 phi2 of t, that also should get multiplied with phi1 of t. Okay, then what I'll do, I'll just expand it. S2 of t phi1 of t is equal to s22 phi1 of t into phi1 of t plus s22 phi2 of t. Phi2 of t into phi1 of t, both will be there. Okay, now what I need to do, I need to integrate it on both the sides with from 0 to t. So integral 0 to t s2 of t into phi1 of t dt is equal to integral 0 to t s22 phi1 of t I can write as phi1 square of t plus s22 phi2 of t into phi1 of t dt. Okay, so what happens here, integral 0 to t s2 of t phi1 of t dt is equal to, here again I'll write integration separately for this term and as well as this term. Okay, so integral 0 to t s22 phi1 square of t dt plus integral 0 to t s22 phi2 of t into phi1 of t dt. Okay, so this will be equal to integral 0 to t s2 of t phi1 of t dt, which is equal to, here s22 is a constant, here also s22 is a, somewhere I have written wrongly, s21 here, s21 see s21 phi1 of t, s22 phi2 of t, s21 phi1 of t. Okay, so s21 is a constant, s22 is also a constant, I'll take it out. So s21 integral 0 to t phi1 square of t dt plus s22 is also constant, I'll take it out. So integral 0 to t phi2 of t into phi1 of t dt. Okay, so integral 0 to t, we know that integral 0 to t phi I of t into phi j of t dt is equal to 1 if I is equal to j, is equal to 0 when I not equal to j. Okay, so see here I have phi1 square, in the sense I and j values are equal to 1, so that this entire thing I'll replace with 1. And what about here, phi1 of t, phi2 of t, so when I not equal to j, its value will be equal to 0, so I will represent the same thing. Okay, so integral 0 to t s2 of t into phi1 of t is equal to s21 into 0 plus s21 into 1. Okay, because it is phi1 square of t, so into 1 plus s22 into 0. Okay, so this will turn to S21 is equal to integral 0 to t S2 of t phi 1 of t dt. Okay, so this I will name as some equation. B I have represented, right? B I have represented. I will represent this as C. Okay, I'll represent this equation as C. Okay, now again let me retake the equation B. What is that equation B I have? Take equation B. Equation B is nothing but, what is that equation I have? This one, this basic equation. Okay, this equation I will retake. S2 of t is equal to S21 phi 1 of t plus S22 phi 2 of t. Okay, now what I'll do, I'll just rearrange this term. So I was telling you, I will rearrange and write it. Okay, so now I'll rearrange and write it. So what I'll do, I'll take this term to the other side. So it will become S22 phi 2 of t is equal to S2 of t. This side, if I take it to the other side, it will become minus S21